In this video, we're going to take a look at sound waves, and we're going to start with tuning forks as seen by the slow-mo guys on the interwebs.
Oh! Can we do that?
I was filming that. Hello, internet. Dan, how's the tune?
Yeah, it's good. I think it's A apparently.
A. Sounds like A.
Sounds like A, definitely. A, yeah.
So I've heard that tuning fork, when you dunk it in water, the frequency vibrates the water in a cool way that looks good in slow-mo.
Yeah, it tickles.
Yeah?
Yeah.
Oh, yeah. So I have some choices for you, Dan. Do you think it will look A, really crap and not good, B, rubbish, or D, really awesome?
Really awesome.
Alright, let's do it. Alright, give it a right whack and
Give
then...
it a right whack. Ready?
Yeah.
Let's go.
Whoa.
Whoa.
You got
Good.
some serious bloody splashback for that, didn't you?
Serious splashback. It's like the smallest little bit of splash in the world.
Oh, that's severe.
Oh my god.
Might have been over exaggeration. Alright.
So what's happening here as the sound wave is produced? Well, if we were to look at a tuning fork and we could see the air surrounding the tuning fork, it might look something like this. As the tuning fork vibrates, it creates different regions in the air around it. And these regions have names. The areas where the air gets bunched together, as we watch this again, these areas are of high pressure, and they're called compressions. The areas of low pressure, or where the air gets spread out, are called rarefactions. So compressions and rarefactions are actually related to waves that we studied in Unit 11. If we were to take a sound wave and match it up to a standing wave or a wave on a rope, we would see that the compressions represent the antinodes. We call these high pressure regions, where the rarefactions are the troughs or the low pressure regions. So you have crest, trough, crest, trough. So if I were to ask you to find the wavelength of a sound wave, what distance would you measure? Well, you should see that you want to measure from crest to crest. So from high pressure point to high pressure point, or you could go from rarefaction to rarefaction. So you could go from here to here or here to measure the wavelength of a sound wave. So if I were to ask you, are sound waves longitudinal or transverse, what would you say? Well, you should say that sound waves are longitudinal. Not only are they longitudinal, but they're also mechanical. And remember, mechanical means that they need a medium. And the medium for sound waves is the air that we live in, the air that's around us. And to drive home that point, I'm going to show you one of my favorite demos of all time. And we'll do this in class. But this is a bell inside of a vacuum pump. And so when they turn the vacuum pump on, it's going to remove all the air from inside, and I want you to listen to what happens to the sound of the bell. watch that demo, I want to point out a couple things. The first thing is, since sound waves are longitudinal, so remember that means that the medium moves in the same direction as the wave. So a longitudinal wave, the air particles move back and forth this way in the same direction the wave moves. That's the definition of longitudinal. And mechanical means the wave needs a medium. It needs air molecules to travel. It doesn't have to be air. It could be helium. It could be something called sulfur hexafluoride, which we'll take a look at. But in this demo that we saw, as the air left the vacuum pump, there was no more medium for the sound to propagate, and so we heard less and less of the sound until there was hardly any air left in here, and we couldn't hear the bell anymore. Now, this green light was on the whole time. The bell was ringing the whole time. We just had no way to get the wave from the bell to our ear, and so we didn't hear it. But the bell was ringing the entire time. When they turned off the vacuum pump and then opened this and slowly let air back in, you heard the bell get louder and louder. As more and more air was in there, it allowed the wave to propagate to our ears. So that's the idea of a mechanical wave. It needs a medium. Last thing I want to show you in this video is how the human ear works. How does it take those waves that are traveling through the air to turn into sound in our brain? And it's a fascinating artifact of our evolutionary history that the ear exists as it does. So watch and I hope you're as fascinated as I am. This is crazy. Think about it. It's crazy. I can talk to you. You can understand what I'm saying because the air molecules between us are vibrating. It's nuts.
Many of us take for granted a very extraordinary organ, our ears. To understand the ear, we need to understand what sound is. The speakers you are listening to right now are vibrating, flexing in and out, causing a wave of pressure through the air. The frequency of these waves, or the speed at which the sound creating surface moves back and forth, affects the pitch of the sound. The level of air pressure in each wave is directly related to how loud the sound is. The outer part of our ear catches these waves. It faces forward and has a specially designed structure of curves, helping us to determine the direction of the sound and also emphasize the frequencies used in human speech. Now that the sound waves are caught, they travel through the ear canal and strike against our eardrum, a thin membrane about 10 millimeters wide. Now that we receive the sound, the middle ear transfers this energy. The smallest bones in your body, the malleus, incus, and stapes, start in motion. The malleus is attached to the eardrum, and as the sound travels along, the force is amplified by leverage until it arrives at the stapes, which acts like a reversed piston, creating waves in the fluid of the inner ear. The most significant increase in pressure is caused by pneumatic amplification. The face of the stapes has a surface area of about...
I'd like you to know these parts of the ear, just for upcoming quiz, but ear flap, the ear canal. So the ear canal, right, is this part of the ear. As sound travels through the ear canal, we'll see it here in a second. Here is our ear canal, and here is the eardrum. At the end of the ear canal, here is our eardrum. You don't have to know the names of these bones, but this is the middle ear. I want you to know that this part of the ear is known as the middle ear, and then this is the cochlea. That this organ where the hearing takes place is the cochlea. So I'd like you to know those parts of the ear because they are vital for understanding how the hearing works in the ear. And it's kind of cool science. So that's it. I hope that was fun. And yeah, if you have questions, let me know.